Okay, welcome back. What I want to deal with today is star and delta connections. Okay, and the three-phase windings of an AC generator may be star connected or delta as previously provided. The important relationship between phase and line currents and voltages is also not shown. Now here we have our star connection, okay, with star point, our current phase, voltage line, current line, etc. Okay, and here we have our delta connection, and you'll notice there's no star point in regards to the delta connection. Okay, let me see if I can bring it up a bit wider, a bit larger. If we want to make it too large, no, it didn't all become over large then. Okay, that's good enough. Okay. Now in regards to current line and current phase, VL equals square root of 3 times VP. The square root of 3 is 1.732. You must confirm this for yourself. Now this is important that you recognize that value because it is constant. Okay? IL equals 3 squared times IP. VL equals VP. Voltage line equals voltage phase. Now, the square root of 3 is simply a constant for three-phase circuits and has a value of 1.732. The delta connection is used for electrical power transmission because only 3 conductors are required. Delta connection is also used to connect the windings of most three-phase motors because the phase windings are perfectly balanced and therefore do not require a neutral connection. Making a star connection at the local substation has the advantage that 2 voltages becomes available. Line voltage of 400 volts between any 2 phases and a phase voltage of 230 volts between line and neutral, which is connected to the star point. In any star connected system, current flows along the line IL through the load and returned by the neutral conductor connected to the star point. In a balanced three-phase system, all currents have the same value, and when they are added up by phasor diagram, we find the resultant current is 0. Therefore, no current flows in the neutral and the start point is at 0 volts. The start point of the distribution transformer is earth because earth is also at 0 potential. Okay. I should say earth is assumed to be at 0 potential just in case there has been modifications to this or the wording since then. It's a bit like some women wants to be male and some male wants to be female. So we have to allow for these changes. A star connected system is also called a three-phase, four-wire system and allows us to connect single-phase loads to a three-phase system. Three-phase power. We know from our single-phase alternating current theory earlier presented, power equals VI cos phi. Okay. Now the W is just to remind me that the power is in watts. Okay. In any balanced three-phase system, the total power is equal to 3 times the power in any one phase. Therefore, total three-phase power equals 3 VPIP cos phi. Now for a star connection, VP equals VL over square root of 3 and IL equals IP. Substituting equation 2 into equation 1, we have total three-phase power equals square root of 3 VLIL cos phi. Okay. And the W is just to remind me that it's in watts. Okay. That's just my little reminder, not for anybody else. Thank you. I suppose I could say to remind me that the unit is in watts. Okay. And again, star and delta connection. Let us now consider a delta connection. VP equals VL and IP equals IL over square root of 3. Substituting equation 3 into equation 1, we have for any balanced three-phase load, total three-phase power equals square root of 3 VL IL cos phi. So a general equation for three-phase power is power equals square root of 3 VL IL cos phi. Okay, that is all. Okay, I'm just recapping here, making sure that it's all in line. Okay, and it can be seen by everyone. Okay, I will pan out in a moment. Okay. Okay, pan back a bit. We got everything in. Okay. Now let us continue. Let us consider delta connection. VP equals VL and IP equals IL over square root of 3. Substituting equation 3 into equation 1, we have for any balanced three-phase load. Okay, and I think I've covered this bit already. So I'm just recapping. Okay, so let's go down and let's look at example 1. A balanced star connected three-phase load of 10 ohms per phase is supplied from a 400 volt 50 Hz main supply at unity power factor. Unity power factor is 1. Calculate A, the phase voltage, B, the line current, and C, the total power consumed. Now let's look at the solution for A. Example 1. VL equals square root of 3 VP and IL equals IP. So VL equals square root of 3 VP. Okay. VL equals square root of 3. Again, I'm just repeating here, and I'm now drawing my line here too. So here we divide both sides by square root of 3. And this is what I've done here. Divide both sides by square root of 3. That cancels out, that cancels out. That leaves me VP equals VL over square root of 3. Okay? And this is what I have here. VP equals VL over square root of 3 equals 400 over square root of 3. And I've brought it down here. 400 over 1.732 equals 230.9 volts. Okay? Now make sure that you write this out for yourself and that you understand the process. Now I've done it like this because this is my style of learning. Okay, you have to find yours that works for you, to make sure that you apply that method in place. Okay, and here we have for B. Now we have here B. For B, IL equals IP equals VP over RP. And the A simply means amps, okay, to remind me of the units. IL equals IP equals 230.9 over 10 equals 23.09 amps. Now, I tended to ignore the 0.09 at one stage, but I found that when you come to do the calculations further on, it matters. So make sure you get it as accurate as you can, okay? Firstly, power equals square root of 3 VL IL cos phi. And here you have the solution, 1.732 times 400 times 23.09 times 1. Why 1? Because it's unity power factor. And here you have 16 kilowatts. Now here you round up. You do not round down, you round up. Okay? It makes sure that it ensures you have the correct size cable to handle the power and the current that it will be transmitted through that system. Okay. Now let me just go back and make sure that we have it all in view. Okay. Make sure that you can read that yourself. Okay. Okay. I'm looking at example 2. Okay. Let me go in closer. A 20 kilowatt 400 volt balanced delta connected load has a power factor of 0.8. Calculate A, the line current, B, the phase current. Okay. We know for delta three-phase power equals square root of 3 over times VL times IL cos theta. The solution for A, IL equals power square root of 3 VL cos theta. And here you have IL equals 20,000 over square root of 3 VL cos theta. Now here we have to transpose to get IL on its own. Okay, so this is where we divide both sides by square root of 3 VL IL cos theta. Okay, both sides. That leaves us with IL equals P over square root of 3 VL cos theta. Okay, I flip it over, giving me IL equals P over square root of 3 VL cos theta. Okay, I call it theta, you call it what you like. Okay, right. Now I brought this here to over here. Okay, let me go up a little bit so you can see what I've done. I'm gonna brought this formula to over here. IL 20,000 over 1.732 times 400 times 0.8. That gives us this value. Now again, check the values, make sure that they're correct. It comes out at 36.08 amps. Okay. Now part B for delta connection, IL equals square root of 3 IP. IL square root of 3 equals, now here we have to cancel out, because we want IP, current line over square root of 3, and here we are, and that's what we have there, 20.83 amps. Okay, so again, make sure you do this for yourselves. Okay, and here we have example 3. 3 identical loads, each having a resistance of 30 ohms and inductive reactance of 40 ohms, are connected first in star and then in delta to a 400 volt 3-phase supply. Calculate the phase currents and line currents for each connection. And here, therefore, here we need to find the impedance, and that we've done. For star connection here, we have VL equals square root of 3 times VP, and IL equals IP. So here, voltage phase equals VL over square root of 3, and here that is all 20.9 volts. Now again, do this for yourselves, make sure that it works for you. I equals voltage over impedance in this case here, and we know the impedance, the value of the impedance is 50, because we calculated it here already. So make sure you know where your information has come from. That gives 4.62 amps. Okay, and that is amps. Okay, for delta connection, okay, again here I've simply transposed accordingly, and we're looking for current phase. 400 over 50 gives us 8 amps, and the current line, etc. Hang on, let me bring, can I bring this up any more further? No, let me just bring this down a little bit so make sure we can get it into view. Okay. 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 Thank you. Okay. Right. Let me just make sure that we got all this in line, in phase. And can we seen? Let me step back a bit. Pan out a bit, I should say. Okay, I'm just recapping the session, making sure that it is visible and it can be seen. Okay. Okay. Thank you. I trust you have a good day, and I trust you found this useful. Bye bye.